So today we are going to discuss a type of respiration. We will go number wise. First of all, type of respiration, muscle. Type of respiration. There are three type of respiration: pulmonary respiration, external respiration, internal respiration. When the airs come, the gases exchange between the lung and the atmosphere is called pulmonary respiration. When the gases exchange between the blood vessels and the lung is called external respiration. The gas exchange between the cell and the capillaries and the blood is called internal respiration. Second of all, muscle help in respiration. For normal breathing, diaphragmic, for when we breathe normally, diaphragmic muscles are enough. But when we do forced breathing, like we are running, we are doing something, we're breathing fast, then some muscles also help us. Like most of the time, these muscles help us. These are stereocleidomastoideus muscle. Then we have pector LS, PECTORALIS, pector LS minor. Then we have SERRATUS, serratus anterior. This is pector LS. These is stereocleidomastoideus, like the neck muscle. These are near the between our shoulders and the chest. These are pector minors, and these are this is serratus anterior. These are present behind the neck, little bit behind the chest. Then we have interior oblique. Interior oblique is the side area on our abs. It's called interior oblique. The transverse abdominal is the line between the abs, and then external abdominal is the side area. And then we have rectus abdominal. Rectus abdominal are the lower abs, like the last abs. These are this. Then internal oblique is the area between the muscles and our side. What do you say? But the side with the sides and the oblique. It's like that. So then we look at the gaseous exchange, like the villi, which help in the gaseous exchange. We have partial pressure, diffusion gas through liquid. Gaseous exchange, partial pressure. It's a Delta's law. It's also we can understand the gaseous exchange more better with Delta's law. As we know, the Delta's law says each and every gases have their partial pressure. Yes, as we know, the Delta's law says gases have partial pressure. So each and every gas has partial pressure, and according to the Delta's law, where the partial pressure is high, the gases move from high partial pressure region to the lower partial pressure region. So basically, oxygen's concentration is less in our body, so oxygen goes in from higher partial pressure to lower partial pressure because the body have less partial pressure, and the carbon dioxide goes out from the body because the body has more partial pressure of carbon dioxide than the environment. Then we have diffusion of gas through liquid. It's a Henry law. According to this, we understand how gases can get dissolved in liquid. So basically, for seeing the dissolving, how fast or how can a gas can dissolve, we have to see on two things: the partial pressure of a gas on a liquid, and then the second thing we see the solubility coefficient of gas, how much a gas is coefficient. Like CO2 is more soluble in blood than oxygen, and that's why it's and it can pass through membranes easily. That's why it can pass through membrane easily, and it gets the pH high. Then we see the volume and the lung capacity. So the volume and the lung capacity is defined as, first of all, TV. What's TV? Total volume of lung. Total volume of lung inhalation and exhalation, as much we can inhale and exhale, like it's TV, total volume of lung. Then we have IRV. I mean inspiration, R mean reserve, and V mean volume. The amount of air a person can inhale after a normal breath is called inspiration reserve. Like we breathe, then we breathe, that's it. That's called inspirational reserve. Then we have expiration reserve. The amount of air the person can exhale normally, that's called expiration reserve. Then we have RV. RV is basically the RV is basically reserved volume, the amount of air which can, when we exhale or inhale, it stays the same. And the plus point, the reserve volume cannot be measured because it's never exit the alveoli. Because for alveoli to function, so it don't go close properly, there should be an little bit of air, there should be something, so it don't go close. So reserve volume never leaves the alveoli, and it cannot be measured. The air which present in alveoli and which cannot be made is called the after the exhalation and inhalation, the after the exhalation the air stays in the alveoli, it's called reserve volume. Then we see the lung capacity. First of all, we see IC, inspiration capacity. When you inhale, after the amount of air we can inhale after expiration, like we leave our air out, then the amount of air we can breathe is called inspiration capacity. Then we have FRC. Then we FRC. Then we have FRC, function residue, the amount of air, the amount of air functional residue, the amount of air remain after normal expiration is called FRC. It is equal to ERV, external respiration volume, plus RV, reserve volume. Then I forgot to mention IC. IC is equal to TV, total volume of inhalation, and IRV, inhalation reserve volume. Then we have VC, vital capacity, the amount of air can be inhaled, the amount of air which can be inhaled and exhaled by a person's or organ or animal's lung is called VC. VC is equal to IRV, inspiration reserve, plus expiration reserve, plus TV. Then we have TLC, total lung capacity, the amount of air in lungs after the normal expiration, it's equal to VC. VC means vital capacity, plus RV, reserve, amount of air in lungs after normal expiration, like we normally breathe and how much air we can exhale. It was how much air we can inhale, and it is how much air we can inhale after a breath, and it is how much air we can inhale normally. That's it. So then we see transport. The carbohydrate is basic. 98% is transported by blood, and 1.5% is transported by plasma. So basically, then it's the form in which it's transport. 75% is transport in the form of bicarbonate, and 23% it's transport in the form of carbohemoglobin, and 7% is transport in the form of plasma. Boron effect said that when the active tissue metabolism produce more CO2, it's going to produce more acid, the pH is going to be higher. When the pH is more high, so its effect pH is less, and then the environment more acidic, it's going to affect the work of the normal functioning, and our hemoglobin cannot bind properly with the oxygen, and it's going to cause the it's going to take the less oxygen to the places where it's need. Then we have effect. We have Helen effect how tissue. It's explain how a hemoglobin take back the oxygen to the tissue. It said that when the hemoglobin takes the oxygen to the cell, so there the amount of hemoglobin is too much. It's release all the oxygen it's used, and the CO2 is too much, so it's bind with the hemoglobin, then it go back to the lung. So then we see how it's bound. Then CO2 goes with H2O, how it's bind with the hemoglobin molecule. CO2 go with H2O, then H2O become H2CO3, and it's released one by HCO3, one bicarbonate ion is released, then the other one go with the form. Then carbon dioxide form bond which hemoglobin, which become the carboxyl hemoglobin. Here I mentioned it carbon hemoglobin. So then it's released an H plus, it become HbCO3, then it's released an H plus and become HBO. That was all for